Hi, I'm Dhagash Mehta. First of all, thanks very much to the organizers to give me this opportunity to give a talk here in this wonderful conference. I'm going to talk about this Fund2Vec, which is a work that I've been working on for quite some time for my own research interest sake with Dhruv Desai and Vipul Satone, both at Vanguard Group. I should mention that these views that I'm going to give in this talk are completely my own views. Vanguard does not necessarily share these views. This is a result of my own research. So let's leave it that. So I'm going to talk about brand new work that we have been working on, which is related to machine learning applied to mutual funds and similarity between mutual funds. Okay. So let's start. Here, I'm interested in this first question. If you are given a specific product, what other products are similar to the given one? Okay. What are the other similar products to the one that you are interested in? The same question, but asked differently. If you have two different products, can you quantify the similarity between these two products? How similar are these given two products with each other? Or on the other hand, how different these two products are from each other? Okay? These are the two very related questions that I'm interested in here. So this is essentially called product similarity, and it appears in different names in different businesses, such as peer analysis, competitors analysis, and so on. Very frequently arising problem in most business areas. For example, a recommendation system. If you are searching for some specific product online, the specific website will start recommending you some similar products that you are searching for. And similarly, in Netflix, if you are watching one movie and you liked it, then Netflix will start recommending you some similar movies. And in our case, because we are talking about mutual funds or ETFs, the problem specializes to finding similar funds or ETFs. In our case, the product means mutual funds or ETFs. I'm going to use mutual funds and ETFs interchangeably for the purpose of this particular talk. They are the same. Just assume that they are the same. So what are the applications of this kind of similarity tool? Let's say you have some hypothetical tool which gives you product similarity for mutual funds and ETFs. What can you do with this? So multiple applications. One, sales and marketing. If you have some salesperson on the field, and then he sees that your end investor's portfolio has some competitors' mutual fund, then the salesperson can run this hypothetical similarity tool and identify the similar funds which are homegrown to this salesperson. So the salesperson's company has certain similar funds that, and then the salesperson can start recommending these similar funds, try to pursue this end investor to replace their existing funds with the homegrown products while retaining the same risk return profile and so on. So that's one example application for this product similarity tool. Second one is alternative portfolio construction. If you again see a specific investor who has a big portfolio of mutual funds, and then but they are all from your competitors, then you can try to create an alternative portfolio which has the same risk return profile as the existing one, except that now you have created your this new portfolio with all homegrown products. There again you can use product similarity tool. Portfolio diversification. Sometimes in a portfolio of mutual funds, it might not be as diversified as you think it is, because certain mutual funds, even though their name might suggest otherwise, are just very similar to each other. Meaning that having both mutual funds would not increase the diversification in your portfolio, rather decrease the diversification. You can run this portfolio or product similarity tool and identify all these similar mutual funds in your portfolio, and then you can do the needful to replace certain funds with others to create this portfolio more diversified. You can also run this product similarity tool to identify similar fund to a chosen one, but with some specific theme. For example, you have a specific mutual fund in your portfolio, but now you want to replace it with a similar ESG fund. ESG is very popular these days. So you can run this product similarity tool and identify a similar ESG fund or any other thematic fund. Competitors analysis. A fund manager would always like to compare how their managed fund is doing with respect to its competitors. And again, the fund manager can run a product similarity tool and identify all the peers of the fund that they are managing. Tax loss harvesting in the US at least, and in probably many other countries, at the end of the tax season, it is sometimes advisable to sell certain mutual funds to realize loss for the tax purposes, and then you can immediately buy a similar fund to still retain the same risk return profile. It's called tax loss harvesting. Again, product similarity tool has clear application here to identify similar fund. The last one, launching new products. Sometimes it's likely that you do not find any homegrown fund which is very similar to the one that is in the market and is gaining a lot of attention. This means that you have some gap in your portfolio of products in your company, and you might want to think of launching a product which is very similar to the one that is of competitors, and then it is gaining lots of attention these days. Okay. So launching a new product by identifying similarity or dissimilarity, okay, or identifying the gap in the market. Because this is so business relevant problem, people have thought about this problem for quite some time, and people have come up with some remedies to do product similarity. The most popular one is third-party categorization. For example, Morningstar or Lipper. These are third-party data vendors, and they have expert committees. They come up with specific categorization for each mutual fund in the market. Each category would have a list of mutual funds, and they all are similar to each other. So if a particular category has 100 funds, it means that all these 100 funds are similar to each other, and it's fairly useful system to identify similar funds. Okay. Here is a problem. So most of the times there are these expert committees who come up with this categorization. They must be using many of the available data, but there is also some inherent human bias that goes into categorization. So many times people have found that certain categories are not reproducible using the same data, using the existing data. Okay. More importantly, here there is no ranking. So let's say you have one specific mutual fund and you are trying to identify all the similar funds to the given one. You go to this one of the categorizations, look up the specific category of this fund, and then in this particular category there might be other 100 funds, which means that you have all these 100 funds which are similar to the one that you are investigating. However, categorization would not tell you which of these 100 funds is more similar to the one that you are investigating. Okay, so that essentially there is no ranking. It just says that all these 100 funds are similar to the one that you are investigating, but no more information than that. The second option is to compute overlap between two portfolios. They are quantified using some traditional indices such as Jacquard index, weighted Jacquard index, and so on. These indices capture the bigger picture, but not necessarily granular details. Okay. The third option is compute Euclidean distance between these two, between each pair of mutual funds in your universe. However, these Euclidean distance don't capture linear non-linear relationship. Okay? They just capture linear relationship. The same thing happens when you compute cosine similarities, which is just another form of Euclidean distance in some sense. Again, no non-linearity here. There are many other unsupervised machine learning techniques that have been explored to identify similar portfolios or similar mutual funds. The ones that have been investigated so far only captures linear relationship, or many times they capture non-linear relationship, but they don't scale well. Okay? They can work with only a handful number of mutual funds, but not the whole universe. So there is a gap here, and that's where we focused on for the last couple of years. Here is our idea. So we formulate the data of mutual funds and their underlying assets as a network. Okay, so we view this data of mutual funds and assets as a network. I'll show you what exactly I mean just in a couple of slides. Then once you have this network of mutual funds and assets, you use machine learning to identify embedded representation, which is a lower dimensional manifold or lower dimensional representation of this very complicated data. And in this lower dimensional representation, all the funds that are similar to each other would be close to each other. Okay? The data points corresponding to these mutual funds will be closer to each other in the lower dimensional representation. I'll give you more detailed explanation of this, but this is an overall idea. We use graph machine learning to identify similar mutual funds. So let's start. So in the beginning, we have mutual funds and their holdings data. And we can get this data from SEC website. You can scrape this data. So here is a typical data set for a snapshot in time. So funds are on the rows. Each row corresponds to a specific fund. And each column represents a specific asset. For example, Amazon, Google, Facebook, and so on. The entries are the portfolio weights of the particular asset in the particular mutual fund. So for example, fund 1 has 20% of asset 1, and hence you have 0.2 in this first entry. There is no asset 2 in fund 1, so there is 0 here in the second entry in the first row, and so on. So this is the tabular data that we have as a raw data from SEC website, for example. So this is our starting point. We have data for all the index equity funds just to make our lives simpler, compared to also adding bonds and stuff. Okay. So we have only index equity funds for now. There are some 1100 index funds and ETFs, and total number of assets was 16,000. Okay. So that's our data. What we did was we put each mutual fund as a red node. Okay, so or red circle here, fund 1, fund 2, fund 3, and so on. Similarly, we also put all the assets as blue circles or blue node. So asset 1, asset 2, asset 3, and so on. So these are our just simple representation of each of the entities in the data. We put link between a particular fund and a particular asset if this asset is within the fund. So for example, fund 1 contains asset 1, so we put a link between them. Fund asset 2 is not within fund 1, and hence there is no link between fund 1 and asset 2, and so on. So essentially, eventually we have this, we start getting to see a graph structure appearing. On top of that, we also know the portfolio weights for each asset for the corresponding fund. So we put this portfolio weights on each link. So asset 1 was in fund 1, and the weight of asset 1 in fund 1 was 20%, and hence we have 0.2 in the first link. Similarly, 0.01, 0.03, and 0.3, and so on. Okay? So these are all the weights on each link. This is eventually then is called a bipartite weighted network. It's a bipartite network because there are two distinct classes of nodes, fund nodes and asset nodes. It is, and a fund cannot be in another fund as a first pass in our data. An asset cannot be in another asset, and hence there is a clear distinction between both these two nodes, and hence it is called a bipartite network. It is a weighted network because there is a weight on each link, and hence it is in general weighted bipartite network. Okay, so and there are many such weighted bipartite networks available in the nature and many other areas of science and engineering. For example, protein networks, genome networks, movies, actors network, flavor ingredient network, and so on. Okay, so bipartite weighted networks are they exist everywhere in nature. Here is the whole data set that we have for mutual funds and ETFs. So 1100 or so index equity funds and 16,000 assets. This is one representation, one pictorial representation of this whole network data set. Probably not too informative, but it gives you some bigger picture of the data. Here is a simpler version of the same data set where we have just extracted a few mutual funds and a few of its assets. And this is how it looks like pictorially. So now go back to the font similarity. That's where we started. What happened to font similarity? Now our problem of identifying similar fonts reduced to identifying nodes which are similar to each other on this network. What is the definition of similarity in terms of network, in terms of nodes on a network? So you can come up with many different definitions of node similarity. This one, for example, is called node degree similarity, which says that if two nodes have the same number of nearest neighbors, then these nodes are similar to each other. For example, node 1 has 4 nearest neighbors, node 2 has 4 nearest neighbors, and node 3 has 5 nearest neighbors. Then node 1 and node 2 are more similar to each other than node 1 and node 3. It's simple enough. You can also extend this definition to more complicated objects such as next to next nearest neighbors. And then in this case, node 1 is more similar to node 3 than node 2 because the number of nearest neighbors as well as number of next to nearest neighbors both are the same for node 1 and node 3. The clustering coefficient is yet another definition that you can think of on the network. Clustering coefficient in simple words is nothing but the fraction of all the friendship networks, friendship nodes in your friend circle. Let's say you have 10 friends. The clustering coefficient is trying to measure how many of your friends are also friends of each other. So out of these friends, how many of them are also friends of each other? At most, there can be 10 choose 2 number of friendship nodes among your 10 friends. However, sometimes not some of your friends are also friends of each other. They don't know each other, except that they both know you. So then you are just trying to compute the fraction of these friendship nodes with respect to the maximum number of friendship nodes. Yeah. And that's essentially clustering coefficient. Clustering coefficient for node 1 is similar to the clustering coefficient for node 2. Okay. And hence node 1 and node 2 in this definition are more similar than node 1 and node 3. How about the community structure? Sometimes two nodes in the same community are more similar to each other than two nodes which are in two completely different communities. So that's yet another definition of similarity. It's called homophily. And in this case, node 1 is more similar to node 2 as opposed to node 1 and node 3. Okay, so node 1 and node 2 are more similar to each other. There can be many different definitions. You can come up with your own definition for similarity on the network. These are, in machine learning terms, are called handcrafted features. You are doing feature engineering here. The whole point of high-end machine learning, the modern machine learning, is that you do not have to feature engineer by hand. Okay. Rather, you should let the machine learning algorithm itself identify all the important features. All you need to do is feed your raw data, and that's our approach. So, so that there is this novel work, not any more too recent. It was proposed all the way in 2016. It's called Node2Vec. It says that once you have a network data, you can use a deep learning approach, especially Word2Vec, and you can identify or you can learn all the features. In other words, you can learn the hidden representation of the data. And once you do that, you can compute the similarity in this new representation of the data. And the similarity will be more rigorously defined. You do not have to handcraft any of these features, and hence your life will be much simpler. Yeah. So that's a crux of this. I do not want to go through the tedious details of this whole algorithm. My main motivation to present this work was to give away this use case where you can apply machine learning for mutual funds, as well as to motivate to start thinking about some sort of mutual fund similarity concept. Okay. So Node2Vec is an extension of Word2Vec. There are a few hyperparameters to create some metadata, in the sense that you are trying to create some new data set from the existing network by doing some random walks on the network. Okay. And how far you should do this random walks, how many random walks you should do, and so on, these are determined by these hyperparameters. Okay. Eventually, you can identify good hyperparameter sets, and then you can create a metric to identify the best hyperparameter set for which maximizes this metric. All these details are mentioned in our upcoming paper. It should be on archive any moment from now. And eventually we also have a very nice hidden representation of the network data of mutual funds and asset. We also identified many similar funds. We also had very interesting pairs of mutual funds, which usually we would not expect them to be similar from the usual methods. So Node2Vec surprisingly came up with a couple of pairs which we were not expecting to be similar. Essentially, what we are doing here is to study the social network interaction, where our social network is made of mutual funds and assets. I'll stop here. I'll take questions. Of course, more details, especially all the plots and tables related to different metrics for Node2Vec for mutual funds and asset network is going to be in our upcoming paper. Please ask me any question, or you can reach out to me or any of our co-authors through this email. And thanks very much.